Are we seeing my slides and hearing me okay?
Excellent. Yeah.
All right. Let me just change this box and there we go. Okay. So, yeah, I was asked to sort of talk about EXES data. It was sort of pitched as an idea of like the pipeline and also just an idea of what you should do if you're just, you show up in the archive and your source that you're interested happens to be there. And so I'm Ed Montiel. I'm an instrument scientist at the SOFIA Science Center, working primarily with EXES, I guess all with EXES these days. And I'm giving this talk also on behalf of Curtis DeWitt, who's the lead instrument scientist on EXES. And just a general note for any things that I have that are links to like things on the SOFIA website, at some point those are going to be migrating to USRA. I saw that Bill Reach talked about this in his talk earlier in the SOFIA school. So just be on the lookout that eventually those will be replaced probably with some type of static URSA link. And so just starting sort of at the idea of some revisiting some different concepts that we heard from both David and Sarah's wonderful talks. Just at the top there, I've highlighted the instrument paper by Matt Richter, the PI of EXES, that gives a general background on what the instrument is. And on the right there is a slide from his review talk at IR 2022, where he showed about how as you move from low to higher resolutions that EXES can do, a lot of more narrow lines start to pop out that you just missed at lower resolution, which was a concept that Sarah showed just recently in her talk. The EXES detector was a 1024 by 1024 array that's basically the exact same material and size of the detector that's in MIRI, just MIRI has more of them for its IFU capabilities. EXES observations were done as opposed to other instruments on SOFIA where they use the standard IR technique of nodding and chopping. We only nodded the telescope. And so your standard pointed observations for nodding were either on or off slit depending on different factors for what you needed. Or for extended sources, occasionally we would map that where we would just move the EXES slit and take it progressive steps depending on what the angle of the slit is on the sky. There was no K mirror to correct for that, so it just kind of is what happened to be at the time of the observation. And EXES has 3 different modes. 2 of them are sort of redundant. They just sort of depend on how much of the wavelength or wave number coverage you got. They were high resolution that delivered spectral power of R, which is the lambda over d lambda that David showed in his talk, from 50,000 to 100,000, and that depended on the slit width that was chosen. Or we could bypass the echelon and just use the cross dispersion grading to do single order modes. And those could give you anywhere from what I quote there, but know that since those were used less frequently, it's just sort of what happens to be in the archive will be the resolutions that you'll find with your data. Another thing or warning and some caveats is EXES data, if you take it from the archive, will be natively in wave numbers, inverse centimeters. And just as a guide, wave numbers are the same as if you take your wavelength in micron, do 10,000 over that number, or if you come from more of a frequency background, your frequency in gigahertz divided by 30, and that's just how you should think about inverse centimeters, microns, and gigahertz. Y units, so if you're plotting your data, if you're grabbing a 2D product, and I'll have some slides coming up, I just wanted to make sure I got some important information at the beginning, and then if you happen to just want to be in the background grabbing stuff, feel free to do that. Our EXES units, so either it's this sort of complicated and mouthful of ergs per second per centimeter squared per steradian per inverse centimeter, or in the new version of the pipeline, we have a bit better handling on how to convert things from that to Janskis. It won't be an absolute scaling. There's still some work that users will have to do that for themselves, but we do have products now that are in either Janskis per pixel or Janskis. And a brief warning about some of the early data was that there was a really high fidelity just conversion from the TEXES pipeline to the EXES pipeline. And so there were some routines and functions that were just literal translations that were sort of, because it was such a big move, were missed and were taken from things that are more specific to TEXES. And so that while those early cycle 4 data, and I'll show why that affects that one more, cycle 4 and earlier, technically, it will say also that those units are in the ergs per second per things, but they're really supposed to be in Jansky or Janskys per pixel. But it's a kind of funky state. So if you happen to be grabbing data that was taken from cycle 4 earlier, drop us an email and we can help sort of guide you on how to get it to the correct state. Or if you were trying to use the new EXES pipeline on that data, we're happy to walk you through it. As Sarah highlighted, I share some databases that are there and also reference Curtis's great talk on how to do it. And Steve Goldman actually has a Jupyter notebook that will sort of try to walk you through doing the atmospheric correction. So if you're in the pipeline or if you're in the URSA archive, which I throw a link at the bottom to, I know Dario had a great introduction for his talk on Tuesday of how to find things in the URSA archive, as well as, or at least for Fifi, sort of how their pipeline works. But so just sort of highlighting what's in there for EXES and which versions of the pipelines it's been used. There's commissioning to OC4M, which ended in January 7, 2017 for that data. That's all been processed, and as of right now, it will only be processed with the sort of first version of the EXES pipeline that was written in IDL. And so just remember that caveat from the previous slide that the units for that, or the numbers for flux conversion, are sort of wonky. Then starting in OC5C to OC90, some of the earlier data is also in sort of this first EXES pipeline, but there was a period where when we transitioned EXES from a PI instrument to a facility instrument, our software team took out a conversion that we just weren't happy with. And so that data are in the correct of the flux, like that part with the ergs per second per steradian, that's all fine and that all makes sense. And so some of that data is not in Janskys at all. And so again, email us if you have questions about which version of that pipeline your data was processed with. And during the closeout, we're currently reprocessing everything from cycle 5 to cycle 9 right now with the new pipeline. And so some of the things you're getting with that will be an improved wavelength calibration, especially for the high resolution data. We're changing our telluric model thing. So previously it was always ATRAN, but we've moved to the PSG. One of the motivations for that is just for like certain regions that there are molecules in Earth's atmosphere that are in PSG that just happen to not be in ATRAN. An example is like we're tired of rediscovering nitric acid in our own atmosphere, that when you plot the ATRAN model, it's like, oh, there's some molecules that aren't there. But when you have PSG, it's like, oh, okay, it's HNO3. And sort of a status. And then, as I said, the flux units are going to be for Cal files, Janskys per pixel. And then for 1D extracted spectra, will be in Janskys. We've already completed OC6L, L, and S. And I've highlighted what's there and sort of the general schedule of where we're going to move through next. If you're grabbing data, there's everything from level 1 to 3 for EXES data. There's no level 2, I think, but basically you can find data that were taken during flight if you wanted to sort of start at the very beginning for your pipelining, if you were interested in that. Then for that, you'd want to make sure you're looking for file names that have psi, dark, or flat in their name. They're in values, just the raw values and counts that we took, and just a quirk of EXES that was chosen by sort of how the electronics box was set up. EXES counts down, so as opposed to like, if you had an unilluminated detector and would expect the flux to be 0 at the thing, and as you expose, it goes up, linearly 100, 200, and so on by every second. EXES started at a fixed value that's typically somewhere around 11,000, and as we expose and more light hit the detector, the value would actually drop. And so something at like 9,000 would be brighter than something at 10,000. In terms of then the different pipelines and what files they produced, IDL produced what I have there for the 2D and 1D things. And then for Python, there's some of the file structure has also changed. And so There's a great table on the EXES manual of what these have in there, and I put a link to where you can find currently where the different pipeline manuals live. And so, sort of showing, so if you're looking to do science with EXES data, which would you look to grab? So for mapping modes, depending on when that data was taken and processed by which pipeline, you'd either want the undistorted product, the UND, where we take out distortion by the optics to sort of put it on a nice rectified style, or CCR or cal files, depending on which units you prefer. So CCRs, the UND used to do both an undistorted and a correction to the calibration, but in the Python version, those are two separate steps. And then the cal is we convert it to Janskys per pixel. And so above there is a map of M82 that I'm just looping through the different slices where you can see the galaxy come in for where neon 2 is brightest, and you can see as the slit stepped across the galaxy, different parts of the galaxy light up at different positions. And on the right there is a preview of the merged order mode, where all the cross-dispersed orders were sort of fit together to make one long spectrum. And for knotted observations, you have different, you have more options, and also if for some reason you were looking at something and wanted to go back to the 2D to see, like, is there a defect in the, on the detector? Is that what caused this, like, sort of noisy region? Or is it just something, that maybe is real and it's just in the 1D? So that's why I say you should sometimes grab the co-added or the calibration file. Similarly, the SPM, COM, and MRMs are new products in Python where we provide that COA with the data. So like basically SPM and SPC, COM, CMB, and MRM and MRD are just all the same versions of the products. Basically, just there's an extra extension at the front there that shows the what the sort of 2D version of that product would look like. So just revisiting back to some resources before at the end, I want to have time to go and sort of show some Jupyter notebooks. We have, again, the typical databases of HyTran, Happy, ExoMol, and GISA that I was most familiar with there. I know David shared some others in his talk, so I encourage you to grab his slides to have those. I wanted to highlight that AstroPy has a spec utils package. So if you're getting started, they have great documentation on that, and it sort of walks you through some of the general tips of if you're coding in Python, how to handle 1D spectroscopy data. And then a reminder about how to correct for the atmosphere, especially watching Curtis's talk. And then in terms of Jupyter notebooks, Steve Goldman, who was the old SOFIA observatory scientist, created some great work, sort of things to get you started with some examples. Curtis and I are also, during this closeout, working on converting IDL routines that we've been using into additional notebooks, and I'll highlight some of those. And I know Sarah just mentioned that she wasn't aware of any sort of currently publicly available things in the mid-infrared that are what she's trying to produce. So rather than also putting her on the spot of always like, hey, this pipeline or is eventually this package will come out, Colette Salick at Vassar College has what she wrote is called Spec Tools IR. I've given the link to her GitHub and then where you can find her Zenodo page to give her credit for her work. And sort of breaking out of my talk, if you guys can still see, so I should be showing you my Chrome set of tabs. So starting with her example notebook, and just sort of scrolling through. So I've run this before to sort of generate what all the different figures that she has, and also because I needed to make sure, like, I have basically what the standard Anaconda download for, I think I stopped at Python 3.7. I know it's up to 3.10, but I know I needed to download other packages like AstroQuery or MC, as Sarah pointed out, and just Googling those Python packages and following their installation instructions gets those installed. And so Colette's example is nicely detailed and sort of walks through. So this is her example of CO in the M band. and it makes, you can highlight the different transitions that are there. She does have a routine that, um, what's as she explains here, basically, it's a thing where you can by eye go through and identify whether or not every one of these lines is a good fit when she does her fitting, but she provides a nice table that already has all of that she's gone through in one example. And as you just sort of go through and read through it, she does other things where she calculates the velocity and finds, if there's multiple components, and will generate a rotation diagram for that. And then she also has other things of like making slab models and how to use that to improve your rotation diagrams. And then she has an example of how MC can be used. Um, and yeah, I encourage people, if they're interested in anything from the near IR, it can be probably customized once you download it to work with your data. I haven't had a chance to try it with EXES data. Um, but, and then also, since I know JWC Miri, she has functions for that as well to help if you're doing proposal writing for that. And then this is the set that will also be posted with my slides I combined a bunch of different IDL routines that Curtis and I have been using and converted them to Python with help from other former EXES members like Maisie Rashman and Amanda Townsend. And so this was a routine that to calculate the Doppler shift to a specific time of year. And I know, as opposed to like other things where like you can write all of these in terms of just external Python packages that you could be called. When I was writing these, I just found it more useful to see the data, and so I could debug in real time between the IDL and the Python. So there's a lot of this, the different math, and I have comments about where these come from. So at the bottom, if you scroll enough, is where I'll get to an example of calculating for looking at the carbon star IRC plus 10216. And knowing that it has a very well documented LSR velocity and an expansion velocity. So you grab the RA index from Simbad. Since we know LSR, there's just a note that you could, if you knew the heliocentric velocity to correct, you could just switch these around and switch this to false. But since we know LSR, we're going to leave this to true. And as a first guess, when I'm looking in EXES headers, I just sort of look at the UTC start and UTC end and sort of try to pick the midpoint of like a leg for when this data was taken. And so just running it as it would generate again, just I print the systemic velocity. And if your source has any additional corrections, like so since 10216 is a carbon star, its outer layers are expanding, so they have their own velocity component. I can just correct for that as well to find that so anywhere between, negative 45 to negative 60 kilometers could be where the gas and molecules might be found towards this star. Plotting again, so make it, and then I have where you can change with this sort of mode between inline and widget. This is just for plotting the data and quickly inspecting it. So you can see here's the PSG model versus the data. And then you can see there's additional features, as Sarah pointed out, that sometimes it's obvious from just the model before you even do a Tolera correction, which I haven't applied here, that there's more features in your spectrum than are in the atmosphere. And then this is where using Hytran online, their program Happy. They have the latest version that you can download and a great manual for how to work through it. They are currently working on a GUI version that they're calling Happiest. That's still, I think, in testing. But moving back, so this is just downloading since beforehand, just acetylene is a known molecule that's been published about in 10216. And so you download a table that it saves, and then to plot it, which this is the synthetic spectrum generator that collaborator Pablo Fonfria wrote originally and has sent to me. And so I converted it to first IDL, then Python. When you run it, and just feed it different values, it will then take these and run it through. And then I wrote this little routine to sort of generate to see, like, did you make it too much? Is there too much, column density, or is the temperature too high? So that you can just step through it until you're sort of satisfied. And then how to plot over it. And then, so in both cases, you'll see that this is the same as above, just with the reading in this test file that I saved out. And how to correct the data is here, where you take the velocity you have in kilometers per second, divide by the speed of light, and then just apply a Doppler correction to both the data. You can either apply it to the data, or like Sarah showed, where you apply it to the shift for your molecule of interest, depending on which one you want to see the data shifted as. And so if we plot it, and then you can sort of then, by zooming in as a first guess, sort of see, like, if you start to see the pattern repeating, as you can see, there's probably more than just acetylene here, and also maybe the initial guess of a velocity wasn't entirely correct, but 10216 is a very rich envelope, so there's definitely more than acetylene here, but this is sort of just as a first guess. If you're working with EXES data and also just want to sort of start with molecule identification. And then I have a routine where I've decided that if you were looking at something that wasn't in high trend, but it was in exomole, so here's an idea what the exomole looks like, where they have all of the molecules that they have. I like looking at it with the two-step, where I see what molecules they have, but then also which ones they have absorption cross-sections for. And so if you were going through, and let's say you were interested in water, they'll show you which species they have, which ones they have. And so usually these cross-sec are the ones where then you'll eventually reach with enough clicking through this table. And then you can put in what they have, like what's the spacing and frequency, your frequency range and wave number, and then how hot do you want the water. So for example, that what I'll have in there is, I believe, 700 to 800. That's 700K. And then for simplicity, I usually default just give me a 2-column file that you can download, this .sigma file. And so as you can see in this example that I have, where I fed in this sigma file, I picked a value for the exponent to sort of generate in this idea of the cross section, and then you fit it into first an exponential, and then it's Gaussian smooth. And yeah, you can then see that it generates sort of another idea of what a synthetic spectrum for, in this case, rotational water would be between 700 and 800 wave numbers. And yeah, that's basically what I wanted to show, and I'll send these to be uploaded, both my slides and talk, and I'm happy to take questions, since this is a bit more open-ended than presenting observations or a theory working with the data.
Thank you very much, Ed. Very informative as well. Nice to take us through the code itself to see what's going on. I didn't see anything in chat so far. Any questions? Feel free to raise your hand or type in chat. Seems like no immediate questions.
No, it's late for people in Europe or further east as well. And like the talk, my and Curtis's emails are there. So if you have any questions when you want to grab data, or you've already downloaded data and want to know more, drop us an email.
Okay. There seems to be really no questions. Okay, Bernard raised his hand.
Yeah, well, thank you for this great overview. I just wanted to say that I mean the amount of material you're showing here is probably overwhelming to many. So if I don't know if you have kind of an overview. I mean, I suppose you're sharing your talk at some point, and I guess a website or so or a page where these resources that you and also Sarah before presented, where they are summarized in also following maybe an astronomer's workflow to some extent, would probably be extremely useful.
Yeah, and I think all like last year's talks, if you go to the old SOFIA School website, like you can find links to these YouTube videos. So I'm assuming something will be done for these, and our slides and my notebooks will be available. Like,
extremely useful. Thank you so much.
yeah.
Yeah, I agree. It could be. It might be also very helpful for students if they want to learn and work with this type of data. Maybe I have a small question. It started a little bit my question with Sarah's talk, but you mentioned also this planetary spectrum generator as a sort of alternative to HRAN, if I understand it correctly. Because when I saw the HRAN plot, and as Sarah pointed out, one of the atmospheric absorptions did not work out very well, or was not fitted very well by HRAN. I was wondering, is the planetary spectrum generator doing better at that, or is it simply also that the how do you call it, the atmosphere in a way, or the molecular abundance is not really well understood yet, and is automatically limited in that way?
Yeah, so I guess with planetary spectrum generator, you have a much wider range of fine tuning. So if you navigate, the EXES pipeline will by default sort of come with one PSG model that's at R 500,000 that we will then try to, based off the mode and slit that you've observed in, or that the data were observed in, we'll try to match that resolution to the best that it can at the start. But users can download then a whole version of models from that cover from 35,000 feet to 45,000 feet at a bunch of different telescope angles. To if they were doing to reprocessing, which we are using that for ours, so the data sort of will have a better matching to initially start, but then you're welcome to go to the PSG website and sort of by tuning different parameters that they have where you can, change the abundances of certain molecules. You can remove molecules if you want, turning on different collisional effects or off, if depending on what you want to do. You can really customize your own sort of routine to get you a better match than will be just by available with the pipeline at the start.
Okay, thank you. Yeah. So it's a very open-ended tool. You can do a lot with it.
Yeah.
Thank you.